Hello, my name is Bruno Zumbo. I'm professor and distinguished university scholar at the University of British Columbia. And today I'm going to guide you through part 2 of the webinar series, Non-Participation, Unit Non-Response and Surveys, a practitioner's guide to the conceptualization, impact of, and adjustment for unit non-response. In part 2 today, we're going to focus on the impact of unit non-response on naive, ad hoc methods of survey data analysis. And we'll talk a little bit about that in a few moments. The outline today, so it's going to transition from webinar part 1 to a webinar part 2 today. Then I'm going to focus on describing the impact of unit non-response using computer simulation. So I'm going to drive a little bit about the purpose and design, and then briefly review some simulation findings for the mean, percent or proportion flagged of survey respondents and regression analyses. In the third section, I'm going to focus on the take-home messages and observations, transitioning to webinar part 3. And then the third one, I'm going to make a couple of comments in the transitioning, taking us to the third and final part of this webinar series, and the references are listed at the end. So let me start with transitioning from webinar part 1 to webinar part 2. Webinar part 1 was a thoroughgoing introduction to key concepts in the field of sample surveys, sometimes simply called surveys. It's important to remind ourselves that the intended audience of this 3-part webinar series is data analysts and health and social researchers who analyze data and are not mathematically trained statisticians. The idea is that there is a small but significant literature on looking at the impact of ignoring unit non-response and using ad hoc methods in the statistical mathematics literature, although even still not a great deal of time is spent there, but there is some literature there. So mathematically trained statisticians can go to that literature. The purpose today is to focus on data analysts and health and social research who are not mathematically trained statisticians, but to analyze survey data in which, of course, non-participation or unit non-responses is quite common. The focus is on demonstrating the impact of ignoring unit non-response in survey research and using complete case analysis. So imagine you send out, let's say we'll see later, 44,135 surveys in our frame. We get back 14,076 of them, leads us to about a 31.89% response rate. It's analyzing those 14,076 respondents, ignoring the fact that there is a great deal of unit non-response. And we do so by doing complete case analysis, meaning we just analyze the complete cases that the respondents give us. And so in this case, there's only 14,076 of the 44,135. We carry on naively as if there was no concern for unit non-response and only use the complete cases. That's the focus of this second webinar, and what's the impact of doing that? The focus is really going to be, or they're really going to address two sort of parts to it: how missing data, in this case unit non-response, may complicate the interpretation analysis of survey data when you're using complete case analysis, and how unit non-response may alter or distort your conclusions from analyses, and by how much, and even when using complete case analysis. So it's to give us a sense of, and to give the participants in today's webinar a sense of what happens if you just ignore unit non-response and carry on. And we're going to learn a little bit, as we saw in part 1, that kind of practice is very common. And so what we want to show today is what's the consequence of that? What's the consequence of doing that? It should be noted that to date, a large portion of the statistical survey research has focused on developing statistical mathematical frameworks and statistical mathematical results on how to think about non-response in surveys from a mathematical point of view, and also developing ever more elaborate and nuanced statistical methods to adjust for non-response rather than documenting the impact of non-response for data analysts and practitioners. So the goal of a lot of mathematical and statistics research is it says, look, it's as if the impact of non-response is widely known and appreciated, and most certainly it is among those working on the statistical theory. Well, they can go on and start developing mathematical results, some new theorems, conditions, conceptions of how to think about and analyze and develop new self-contained mathematical results for the sort of fundamental theory of survey data, including a very old literature on adjusting it for complex survey results, and even a literature on adjusting for unit non-response. The focus is that mathematical statisticians really will note that there's a potential bias and then move on and focus on providing solutions, developing theory to what is known, but at least for applied researchers, widely undocumented statistical problem. But for mathematical statisticians, they don't necessarily need to look at the impact and the consequence of unit non-response in a variety of settings. For most of the motivation, it's sufficient to say there are biases and to carry on developing the new statistical methods, the new statistical theory. Nearly all introductory texts to non-response remark or describe, to some extent, the potential biasing effect of non-response. In contrast, however, data analysts are, for the most part, asked to take the impact of unit non-response on faith. So a few sentences in nearly all introductory texts, many papers, review chapters, they remark briefly, maybe a paragraph or two, or even a short section, describe the potential biasing effect of non-response. And then one carries on in the development of the theory. And data analysts are expected to take the impact of unit non-response on faith. And by this, remember, it's the impact of unit non-response when one uses sort of ad hoc approaches, this complete data, complete case analysis. In contrast to all of this, remarkably, in a systematic review of 262 studies published in 2010 in 3 leading epidemiologic journals, complete case analysis, ignoring unit non-response, was reported in 81% of the studies. That's in a 2012 paper that we cite here. That's remarkable. It shows that even in epidemiologic journals, and to be frank, those are often fairly technical, rigorous journals where they report some rather complicated analytic methods. And even in those settings, 81% of the studies ignored unit non-response and just did complete case analysis. That, to me, is a marker of the fact that there is a gap, that in fact, certainly mathematical statisticians and statisticians like myself, yes, we recognize that there is a biasing effect, but data analysts, and including epidemiologists in this case, and you'll see this sort of technique and this sort of method, this sort of approach where a large portion of the papers ignore it. You'll see that in a lot of other social behavioral health sciences, not just in epidemiology. As noted in part 1 of this webinar, similar patterns of behavior among data analysts can be seen about, for example, the impact of outliers and robust estimators. John Lind and I in 1993 noted there's likely both an implied continuity principle, that is, small deviations result in small problems, as well as the lack of easy-to-use software. Both of these are contributing to this ignoring, in that case of outliers, in this case of ignoring unit non-response. But it's the concept is in a sense the same, in the sense that there is an elaborate theory that's available to mathematically trained statisticians, but when you look at the day-to-day practice, this new theory, these more nuanced, subtle ways of correctly analyzing the data is largely ignored in day-to-day practice. Things are improving, but even still, even you see in this 2012 paper where they reviewed 262 studies, 81% ignored unit non-response and did complete case analysis. Complete case analysis, just to remind ourselves, is just simply, it's an ad hoc method in which individuals, you analyze and you report with just the data at hand, whoever responded, and ignoring unit non-response entirely. And you're using conventional statistical methods that do not adjust for the unit non-response. That's what complete case analysis, that's what I'm talking about here, and that's what we're dealing with. We want data analysts to get a sense of the impact of doing this kind of naive analysis. Our remarks on the previous slide should not be read as a criticism of statisticians or others working in the area of survey statistics. And like I said, this happens in outliers, it happens in other areas. It's really not a criticism because, frankly, the statisticians working on statistical theory, providing solutions, all they need to carry on their work say there is a biasing effect. Instead, our remarks are observations that more focused attention needs to be given to demonstrating to day-to-day data analysts what the impact may be of non-response and when, and to provide the motivation and setting for the three-part webinar series and really part 3. And part 2 here is a kind of knowledge mobilization aimed at the production and use of these research results, including knowledge synthesis, some transfer exchange, and a co-creation by researchers and knowledge users. And this speaks well to the collaboration here of Dr. Woitschach, who's my postdoc, who's an outstanding data analyst and social and health researcher and psychometrician, collaborating with myself, a mathematical scientist, statistician, and psychometrician. It's this collaboration that we believe leads to the kind of knowledge mobilization, which we will hope draws more attention to day-to-day analysts on the impact of applying ad hoc complete case analysis when you have unit non-response. In part 2 of the webinar, some of the concepts introduced in part 1 will be described a bit more formally, intending to provide data analysts insight and intuition into the impact of unit non-response and how to transition to part 3, choose and apply a method to adjust for non-response. Again, this intended audience, who may not necessarily be mathematically trained statisticians, keeping that in mind, we do not attend to details of mathematical notation and proof. There is a literature for that, and I urge you to take a look at that if you have that kind of training. Instead, we'll use computer simulation and a bit of formalism to help provide an intuition for the impact of unit non-response when you do complete case analysis, ignoring the unit non-response in survey data. And the purpose then of part 2 of the webinar is that we will demonstrate how ad hoc solutions like complete case analysis are not a good idea in general for day-to-day data analysis practice. This motivates us to see part 3 of the webinar series, where alternative methods for adjusting are described and methods are demonstrated using 2 statistical packages. Practice data is made available and tutorial results are shared. So this is the bridge between the thoroughgoing introduction to survey methodology and unit non-response, to the bridging to the demonstration of what options are available to adjust for unit non-response. This is the motivating bridge between them. Let me bring up a few concepts that I want to remind us of, give it maybe a little bit more formalism than what you saw in part one, building your knowledge base. There is a propensity of a sample unit responding to a survey. That propensity is a latent variable that is therefore not directly observed and needs to be estimated. So the idea here is that there is a propensity for a sample unit individual to respond to a survey. That propensity is a latent variable that is therefore not translated. And it's often think of it as sort of a probability. What's the probability that in the sample frame, every individual has, in a sense, a propensity, which you can quantify as a probability of responding to the survey. The response behavior is connected to the participant's interests and willingness to participate. We saw this in seminar one, and it's not a fixed property. It can be generalized to all survey context. We then think about response models that can be based on ancillary or auxiliary information, but they can also be based on non-response theory. So you basically want to have some sense of the response models, that is, the model behind the probability of responding or the propensity. So what you have is, if you imagine every individual in the sample frame would have, or every respondent who sent a survey, they have a propensity of responding. And we're actually going to talk about different causal mechanisms for non-response. And those mechanisms, in fact, build on this notion of a propensity of a sample unit. Sample unit in most of our cases will be individuals, but they don't have to be. They could be organizations. They could be subgroups of organizations that are sampled. But for our sake here today, let's think of it as individuals. So every individual in the sample, who's the sample unit, they have a propensity of responding. And in a lot of what we're going to do, and we conceptualize unit non-responding or missing data generally, it builds on this notion of a propensity, which is quantified as a probability of responding. And of course, these probabilities can be sort of modeled through ancillary data, but they can also, it's very important to get a sense of non-response theory. And that's one of the messages we're going to learn, that, having theoretical understanding as to what drives the propensity for a sample to respond is really important work. There's some work in this area in the literature, but far more needs to be done. Now, recall that there are two broad frameworks described and used in the survey statistics literature. You'll see the finite sample population framework. In that framework, all the units of the population are identifiable, which is not necessarily the case in the infinite population framework. I'll give you a sense of how we move between those a little bit. Our focus is on unit non-response, which translates to non-participation in the survey. The concept of representativeness is one that we hear some in the social science literature and the health sciences, but on its own, it's not enough to provide a thorough study of non-participation in surveys. So we've seen, and we hear some discussion of, representativeness. On its own, this notion of representativeness is not enough. We need a bit more of a richer framework. And that's what we like in the previous notion of a propensity of a sample unit and these response models. And also bringing into this notion of finite populations or infinite populations sort of frameworks. So representativeness on its own is not sufficient for how we want to think about it. And I'm hoping data analysts don't find it sufficient as we move to this more nuanced way of thinking about it in terms of every unit, in our case, every individual, having a propensity to respond. A very important concept central to non-response, and if you continue to study survey statistics, is the notion of auxiliary information. You also see the term ancillary information. For the moment, let's not spend too much time on that distinction. However, the term auxiliary information is used somewhat inconsistently in their survey statistics literature. Or by inconsistency, I really mean that it's used in subtly different ways, pointing to the same phenomena. So, but the most common use includes any information not directly linked to the survey. So you have a survey which has a certain number of questions on it, or items if it's in survey questionnaires. Ancillary information is information not directly linked to the surveys, not in the survey itself. Things such as the population total of a variable, the mean in a domain of a variable, or information that is available prior to data collection, and this information is known for all units of the population or known for all the sampled units. This ancillary information, this is a big term, it covers a lot of different things, but it's the idea is that it's not in the survey itself. It's not directly linked to that survey, which means once you get the survey back, as Dr. Woitschach mentioned in part 1, you would then have a data file that has the unique identifier for every individual in your sample frame. Then you would know who did not respond, and then you could, well, at least you know you have an identifier, and you can then get this ancillary information. In our case, could be data from a different data file, some sort of, I think of it as some sort of administrative data, and that you have the approval to link them through this unique identifier. So now in this data file, as Dr. Woitschach mentioned last in part 1, you would have a sense of who responded, and you would know a little bit about them in terms of this other ancillary variables. This auxiliary information. Auxiliary information, however, is really a lot of other things. And so things like if you knew ahead of time the population total of a variable, the mean in a domain. Now, typically point estimates are generated for specific domains of interest, and a domain may be the entire population or any specified subpopulation for which estimates are designed in the survey purpose. So you could have auxiliary information that is things like the population total, the mean of a variable, the mean in a domain of a variable. And population total, you may know, for example, in a particular subdomain or domain, you may know the total income. So that variable could be used in planning or analysis of the survey data. Anything that could help your point estimates. So ancillary information has a lot of different uses. For our case, in terms of unit non-response, typically what we have is that its information is available prior to data collection, and this information is known for all units of the population, are known for all the sampled units. And then there has to be some data linkage because it's separate through a unique identifier. The second kind of auxiliary information, variables available prior to data collection, will feature prominently in considering missing data mechanisms, ignorable settings, and applying adjustments for unit non-responses. So this notion of auxiliary information is really quite useful, although it's not immediately relevant to our purposes. In the webinar series, it's worth noting that this auxiliary information is also used at various other stages, survey design, to improve the efficiency of sampling, and the survey estimation stage to construct accurate estimates. And this is, again, I want you to get a sense for this notion of auxiliary information. Auxiliary data can be derived from other sources outside the survey. For example, such as regularly updated administrative data sources or annual totals from a larger independent survey. In the cases where the auxiliary data are correlated with the variables of interest, the additional information can be incorporated into the estimation process using ratio, post-stratification, regression, or rating ratio methods. So this notion of auxiliary information, although we have one particular use of it, it actually has a lot of other uses in survey statistics, and it's worth knowing a little bit about it. These estimates, using this other information, maybe you do raking ratios or raking ratio methods and post-stratification methods are still very popular as our regression methods. These estimates can be derived by creating sort of additional new weights that bring you as close as possible to the original design weights according to some sort of distance function or metric. So there's a whole literature in that in the sample statistics literature that gets into it. Not directly what we need to do today, but I think it's worth you noting that this auxiliary information is used for other things, not just adjusting for unit non-response. And statistical agencies will have ways of getting this auxiliary information and with ethical approval, being able to do certain matching that then allows them to do either analysis for adjustment for units non-response or some of these other more interesting things in terms of planning and sampling and constructing accurate estimates. Please note that we'll discuss the impact of unit non-response for both descriptive and analytical survey studies. So most surveys at statistical agencies are conducted to estimate means, totals, ratios based on the measured variables and change over time in these parameters. And that's the sort of descriptive kind of analysis. There's a growing interest, however, in the use of statistical surveys to fit statistical models used using regression, structured equation modeling, or more complex mixed models. And that's called analytical studies. So there are both descriptive and analytical surveys. And today we're going to see both of them. In order to demonstrate to day-to-day researchers the impact of unit non-response on conclusions from survey data, and along the way shed some light on apparent contradictory conclusions in the literature, a bit more intuition about MCAR, MAR, and MNAR, that is missing completely at random, missing not at random, missing at random. So MCAR is missing completely at random, missing at random, MAR or missing not at random, MNAR. So we're going to get a bit more of intuition and what this notion of ignorable as well as non-ignorable or non-ignorable statistical settings I think is very helpful. And we're going to take a look at these concepts from sort of probability and modeling point of view and a little bit of you can see some graphical description, and I'm going to build it even further into the context of computer simulation methodology used in this seminar. What's interesting, I think it's important to get a sense and you learned about these sort of mathematical models for the causes of missing data. You know, MCAR, MAR, MNAR, I think are incredibly powerful lenses through which to think about the response process and to think about this propensity of responding. And this leads to this ignorable and non-ignorable statistical settings. And just right off the bat, I'll tell you right now, non-ignorability is most clearly connected to missing not at random, to the MNAR, where MCAR and MAR are often conceptualized, MAR is often conceptualized as ignorable. And we'll learn a bit more in a few minutes what that means. All right, let's now move to the second section today, which is the largest chunk of the webinar, which is demonstrating the impact of unit non-response using computer simulation. And I'm going to start by giving us a little bit about the purpose and design of the simulation. And I'm going to describe the methodology, and I have a little subheading here. A funny thing happened on the way to investigating ad hoc methods. The surveys that have non-participation or unit non-response. It's a bit of formalism about some key concepts in sample survey statistics and non-response. The value of computer simulation for our purposes is really something that I want to shed a little bit of light on. think of computer simulation as doing the mathematical calculations for us. If we were to present this from a lens of statistical mathematics or math stat, then we'd be using the mathematics to try and give us a sense of, again, intuition for an understanding for the impact of unit non-response on these ad hoc complete case analysis. And there's some very lovely research in the statistics literature that goes back decades that doesn't entirely that. But you need the language, and you need a familiarity and comfort with some mathematical methods and probability. Well, our hunch is that the lack of studies centered on communicating the impact of non-response in surveys to day-to-day analysts and researchers may be partly due to the nature of the observational studies, where we do not have access to the respondents' complete information. All I'm saying here is, in this obvious way, when you run a survey, you only have the data you have. You do not have, in a very trivial sense, any information about the responses to those surveys from the people who did not respond. That's obvious, but that point really is, I think, a major hurdle in trying to get a sense with day-to-day data analysts on the impact of unit non-response. So, find that in this setting, computer simulation functions as a kind of demonstration experiment. One collects data using the computer simulation. One mimics, if you wish, the simulation process. So we have the steps of the simulation you'll see in a bit actually have a sort of target population. We have a frame. We have then surveys are sent out, and we have the respondents. But in the simulation, because it's a computer simulation, we also know the values of the missing data because it's in a simulation. Unlike in a setting of observational studies, you don't have them by definition because they're missing. Therefore, in this setting, computer simulation functions as a kind of demonstration experiment. One collects data using the computer simulation. In essence, the simulation helps us calculate the impact of unit non-response in a traceable empirical manner. The simulation, in essence, mimics what happens when one conducts a statistical survey. However, in a simulation, we know the population parameters and the simulation design, the experimental conditions, if you wish, are selected to demonstrate the impact of certain kinds of simulation. So we will simulate missing not at random. But so the computer, in essence, goes through, in a sense, does the full survey, but we have in the computer experiment, in the demonstration, what people would have responded, what survey units, people or survey units would have responded on the questions of interest, which of course we don't have in observational data. And I think that's been a major hurdle for communicating the impact for day-to-day data analysts. And our aim is to use the computer simulation, the demonstration, to give day-to-day analysts this intuition. They're doing, in a sense, this experiment. So we simulate administering the SF-36 and focusing on the mental component scale. And this will allow us to demonstrate and document the impact of unit non-response in survey research by analyzing simulated data that mimics a health-related research context. We're going to simulate a health survey using the SF-36. You saw a brief description of it in part 1 of the webinar, focus on the mental health component. I think that's sufficient for what we wish to do. You'll see this kind of information in any text on survey design, survey planning. So on the left-hand side, you'll see a description of planning and conducting sample surveys, and beside it, a parallel in our computer simulation, more or less. So when we're planning, we think of sort of our target population. If you wish, it's our inferential population to which inferences will be made by researchers and readers. let's not get into the finite population versus infinite population, the various other kind of models for the moment. Let's just, for the moment, think of ourselves having a sort of target, and if you wish, call it a population. Where the planning begins then is you, in the target, the group for which the researchers would like to make general statements, define a target population, and you get a frame, a list to sample from. Using some sort of probabilistic sampling to compute sample size for targeted margin and sampling error, proportions, means, etc. We have the frame, which is the list from which the sample is drawn. Now, to be very clear, throughout today's webinar, we're going to strip it down to a very basic kind of sampling. So there is no complex survey or complex sampling that we're using in our simulation. The points we want to make can be made very simply by assuming, very trivially, a simple random sample. This could be redone if you wish, the simulations with complex survey designs, but I think the complexity of that, I don't think adds anything to our point. I mean, our point can be seen very easily by, rather than any complex survey design with strata or clustering, we're just doing simple random sampling in that context. So our frame is a list from which the sample is selected. In our case, in our simulations, it's going to be through an SRS, simple random samples. Then we have in the next stage here, the survey, those selected from the sampling frame follow probabilistic sampling are sent the survey. And then we have survey respondents, those responding to the survey. And in nearly all cases I've ever come across, there are a certain proportion, a certain percentage of individuals who do not respond, who do not participate at all. And that's our unit non-response with a particular non-participation or participation ratio. In a simulation, we have a similar kind of idea going on that's mimicking it. Again, we could develop a more sophisticated simulation algorithm, but I think it's sufficient for the points that we want to make. We have our target populations, we have population parameters and characteristics and even ancillary variables. And then we have an implied frame in the simulation process, the list from which the sample is selected. And this is important to remember that this is the data if everyone were to participate. That is, there is no unit non-response. And this is where the glitch is in the previous slide here, where we said, look, in observational studies, we don't have this. Right? What we have is the survey respondents with non-participation. In the simulation, this target populations and the setup of the simulation gives data if everyone were to respond and everyone were to participate. So we will have in our simulations the complete case, which is really the implied frame. And we'll also have survey respondents with non-participation reflecting different kinds of non-participation through, missing at random, missing completely at random, or missing not at random, etc. So the simulation reflects these three. There's the population parameters. We then get our implied frame in a simulation process. This is the list from which the sample is drawn. Sample selected. This is the data if everyone were to participate. We actually have the survey responses and then we impose and then we remove according to whichever Missingness plan. We get our survey responses with non-participation, that is with unit non-response. Just to remind you, you saw this in part one, we're simulating a health survey using the SF-36. We wanted to use something that is widely used in the health research and social research domain. The SF-36 is very popular. Just to remind people, there's 36 items. They have all these subcomponents. The mental is made up as vitality, social functioning, role, emotional, mental health. And all domains are scored on a scale from 0 to 100, with 100 representing the best possible health state. And as you saw in part one, of the webinar is created by weighting of the psychological subscales. So you've got this vitality, social functioning, well, emotional, mental health into this mental health score. The setting of the simulation, what variable is the focus? That what is being measured? Well, we're mimicking or simulating, administering the SF-36 and focusing on the mental component scale. Our imagined target population is community dwelling Canadian adults. Sufficient, again, for our purposes today, just as a demonstration. And to simplify the simulation, our sampling pan, as I said earlier, was a simple random sample. Some useful basic statistics for the simulation to make the population characteristics plausible. They have a mean around 50, 51, and a standard deviation of 9.1 based on a Canadian normative sample. And this is the Hopman et al. In 2000, the Canadian Medical Association Journal. And we used some of those basic statistics as population parameters in our simulation just to make it, have it a feel of plausibility. So, you know, people can envision, people can imagine the SF-36 being administered, right? There's a population, there's a sample, there's a frame, an implied frame. We have, in this case, not only is there an implied frame, but because it's a simulation, we know everyone's score on the mental component. Then we mimic sending out the survey, and this sample is only individuals who chose to participate. The others, we have unit non-response, and we simulate that based on missing complete at random, missing at random, missing not at random kind of frameworks. Throughout the simulation, we are computing the naive complete case analysis. That is, what are the outcomes if one ignores the unit non-response and computes the statistic of interest based only on those who responded without adjustment using conventional statistical methods. So if we calculated means, it means in a confidence interval, a proportion confidence interval, or a regression analysis, using just conventional approaches, ignoring the unit non-response, this complete case analysis. And as we saw earlier in the presentation today, this happens this is quite common. I mean, in those epidemiologic journals, 81% of the time, this is precisely, and this naive and computing of naive complete case analysis is really, this is something we want to, we'll show you by the end here, persuade you there actually is some problem doing that. It is not good practice. This ad hoc approach is not good general practice. There are subtleties, and that's the point I want to bring this, and that's the complexity of this issue. Well, we're going to be computing the typical naive variance that ignoring unit non-response, so the mean and confidence interval for the mental component score, very common in sort of what we described earlier as descriptive surveys, the portion of respondents and the confidence interval for the proportion, to identify the presence of either depression or anxiety. And there's a cutoff in a published article that we cite there that says, listen, if you use, remember it's 0 to 100, the average is 50. If you use a cutoff of 38, what they find is that this is and there's other cutoffs, but this one's been used to sort of identify or flag for basically mental health issues, so depression or anxiety. And it's used to sort of track this proportion over time or to report it for domain or subdomain. And you'll report estimates in a confidence interval in these descriptive surveys. And we'll also do the analytic surveys in which we regress the MCS score on 3 predictor variables. And I'll show you what are the issues when we do those analytic surveys there in our simulations. Just to be clear, we're going to be varying 3 levels of response rate, 31.89%, 15.95%, and 7.97%. These are numbers, at least in some extent, we'll see in our practice. Dr. Woitschach and I have seen, 31.89% is a very common number we saw in a recent survey. So imagine we have here 44,000 135 Canadian adults were sampled. That's our frame, if you wish. And you might get a 31.89% response rate, a 15.95%, or a 7.97%. That's a small response rate, but remember, this is a response rate. So only 7.97% of these 45,000 responded. The other ones chose not to participate and in fact are unit non-response. We think about 3 causes of unit non-response following the conventional literature: missing completely at random, missing at random, and missing not at random. Not at random, let's not forget, this is our non-ignorable case. We'll see why in a bit. We also thought we would vary the distribution of the mental health component scores. This was particularly the case for the case when we look at the mean and the proportion. So there's a normal and there's a non-normal distribution that we look at. So we have these different response rates, all of these 3 causes, and normal distribution and non-normal distribution in the cases of the mean and the proportion, the 1 sample cases. Then in the regression case, we still have some of these factors in there, except we're going to look at specified and misspecified regression models there. So, we're going to look at MCAR, MAR, and MNAR forms of unit non-response, or causes of unit non-response, or patterns of unit non-response. And we're looking at correctly specified and misspecified regression models. And again, we'll give you more formal definition of that, of what we mean by them in a few moments. A bit more about the setting of the simulation. We looked at, as I said, 3 different response rates. Imagine 3 surveys in which 44,135 adults were sampled, a total of 14,076, 7,038, or 3,519 responded to the survey. So that's how we have our 3 response rates. So of the 44,000, 14,076, of the 44,000 in a different survey, 7,038, and of the 44,000, 3,519. And just to give you a sense, one is the sample size of respondents. The sample size of unit non-respondents in this one example is 30,059. So far more individuals did not respond than responded. And the total number sampled is 44,135. So the proportion that responded are defined as N1 over cap N. That's 14,076 over 44,135, where cap N is N1 plus N2. And that gives you your 31.8% response rate. In all cases, far more individuals are selected to not respond than did respond. Again, this was done purposefully as part of our demonstration. I've certainly seen in my own practice over the last 30 plus years, response rates in social surveys outside of agencies like Statistics Canada, Bureau of the Census, GISIS and other sorts of, or Health Canada, the Bureau of Labor Statistics, et cetera. Those places will have response rates that are higher than this case because they'll do certain, these are agencies that do this, on a regular basis. But I've seen certainly a lot of research surveys that are in the 15 to 8% response rate. We'll find out in a little bit whether response rate is important or not, which is the reason why we chose a couple of them. I want to say a few words about the mechanisms of missing data, because that's why we've moved to this language rather than the notion of representativeness, where some individuals like to work from the language. This gives a certain mathematical structure and some bit more formalism. I really like Daniel Newman's 2014 description, and in fact, so much so that I'm not sure I can improve on Newman's description. So let me, with credit to to Newman, and the citation is there. Let's describe the three mechanisms of missing data. Random missingness in MCAR, missing completely at random, and systematic missingness in MAR and MMAR. And immediately, this is an important distinction to pick up that I builds on perhaps something that you learned when you first were introduced to this concept, is that the random missingness is MCAR, the missing completely at random, and systematic missingness is missing at random and missing not at random. MCAR is missing completely at random, and as you can see here, it's a sort of Rubin's terminology. Schaefer and Graham is an absolutely lovely, and little Rubin as well, but it's Rubin's 76 typology. So the missing completely at random is that the probability that a variable value is missing does not depend on the observed data values nor the missing data values. So missing completely at random is it depends on neither the observed data values nor the missing data values. So in this case, just imagine the questions for the mental scale of the SF-36. What this is that the probability that a variable value is missing does not depend on the observed data nor the missing data. And the fundamental idea here is that every unit, every individual has a propensity for non-responding. We're going to quantify that and we're going to characterize that propensity in terms of a probability, which is a latent variable. It's not observed. The missingness pattern results from a process completely unrelated to the variables in one's analysis, or from completely random process, similar to flipping a coin or rolling a die. So in this case, the probability of a value being missing, given the complete data, equals the probability of it being missing. So think of it as every individual not only has a propensity, but in this case, the propensities would be uniform, or the probabilities would be uniform. Missing at random. In this case, the probability that a variable value is missing partly depends on other data that are observed in the data set, but does not depend on any of the values that are missing. So it does not depend on the level of MCS score, that is the mental health score, but it does depend on other data that are observed in the data set. So in terms of probabilities, you see the probability of it being missing for any value given the complete data equals the probability that's missing given the observed data. So that's missing completely at random. It's a bit of a funny term, but we'll come back to that because it doesn't, random in this case is used in the statistical and probabilistic sense, not in the lay sense. And so it confuses some people because in fact, there is systematic missingness when we have missing at random. And then we have MR, missing not at random, is the probability that a variable value is missing depends on the missing data values themselves. So in this case, you might have we have a mental health score. The probability of the missingness depends on the level of the mental health score itself. So individuals who are very low in mental health, they in fact might have a much higher probability of not responding. I'm not a clinician or any such thing, but you get a sense that in terms of very low mental health, and you might have high levels of anxiety or depression, you may not likely want to participate in a survey, and that's the whole notion that MNAR means that it's dependent on the variable itself. So the probability of a value of a variable being missing given the complete data does not equal the probability of it missing given the observed data. And you can see why these are it's going to come back here. These definitions are based on complete data, which in practice, we do not have. In simulation, we do, but not in practice, not in actual surveys. And that's why here I want to use simulation to give you a sense of this. So of these three, one is random, missing completely at random. It's the MCAR mechanism. And the other two are systematic, the MAR mechanism and the MNAR mechanism. Newman goes on to say that they highlight the seemingly odd labeling of the MAR mechanism. Despite being referred to as missing at random, MAR is actually a systematic missing data mechanism. The MAR label is confusing and stems from the unintuitive way that statisticians versus health researchers or social scientists would use the word random. To a statistician, random is based on a probability distribution, an unknown outcome of a random variable. The important thing to keep in mind here as well is that, and quite often, and this is an extremely subtle idea, people will think of MCAR, MAR, and MNAR as sort of distinct categories. They're actually not. They're actually not. If you read a bit more and dig into it, you'll actually see that they actually are not as distinct as you think, not all of them anyway. And you'll get a better flavor for MCAR, MAR, and MNAR, at least as mechanisms on how to think about conceptualizing, in our case, a unit, sampling unit, choosing not to participate and not respond. Newman does a very nice job here building on a sort of a graphical depiction of this. And a line, so you imagine that there are two variables, X and Y, where some of the data on Y are missing. And so MCAR says that, so you have in this, so there's a sort of a description, a graph. A line means that they are, in fact, that they are correlated. They're correlated. And so, or there is a relationship, perhaps, an association. So in the MCAR case, there is no association between the missing, missing Y, that is, it's a dummy variable, indicating whether someone has responded or not responded. That dummy variable in MCAR is not related to either X or Y, and Y is the variable of interest that has where there's some missingness. So the only relationship is between X and Y, and that's completely at random. Let's now look at MAR, missing at random. This dummy missing variable mechanism, or if you wish, that propensity that we talked about, now manifested it as a 0-1, if you wish, or even as a propensity, but really it's easier here as a 0-1, but it can even be a propensity itself, a probability. It's related to X, but it is not related to Y. It's when the missingness is related to Y, that is, as we said, low levels of depression are less likely to want to respond to the survey, so that it's not equal for all levels of the domain of the variable of depression. This relationship results in MNAR. And that's the key element here that you don't see in the MAR case. I think there's some intuition. I'll point you, I would strongly recommend the Newman paper. All right, well, let's do a little bit of findings from the simulations. And let's first talk about the mean. Let's do the single variable case. We'll look at the mean of the mental health, of the MSC score and the percentage flagged using the MSC score. So we're going to simulate administering the SF36 and focusing on the mental component score. Remember, all the domains are scored on a scale from 0 to 100, 100 being representing the best possible health state. The mean of the MCS of the mental component score tracks the average depression or anxiety level. In a Canadian normative sample, we saw in the 2000 paper by Hotman et al., an average of about 51.7 and a deviation of 9.1. We worked with those general values to give us a sense of what to simulate. There were two types of distributions that we looked at, and both distributions have the same mean and standard deviation. So on the right, you'll see a normal distribution, this bell curve, and on the left, if you're looking at the screen, I wanted to have a non-normal distribution, and the distribution I chose, of the many possible I could have chosen, is a member of the family of sine H arc sine distribution. This is a family distribution that allows us to control the skewness, tail weight, and moments. And so I could have the same mean and standard deviation, but you'll see that, in fact, this one is highly skewed. And I thought, well, it's quite possible that in the general population, we might have this. We might have that a lot of the scores are bunched up towards the higher end, around 60 here. There's actually more to it than that. But that they trail off as we head towards the low end, right? Meaning there are very few with individuals with mental health scores that are on the low end of the distribution. And so cutoff, so when you'll see a cutoff next, you'll see cutoff is about here. It's at 38. So anyone down there might be flagged as, at least for the purposes of population health, they might be flagged as having a propensity for depressive symptomatology or some such thing. So imagine Y is the MCS score and X is an ancillary variable that is related to Y. I looked at three types of unit non-response as well as the complete case. Now we have the simulation, so we actually know all the data that is missing. We actually know it because it's a simulation, because it's removed in the next stage. So we actually can keep it. So we have the complete case. So this is what makes it very unique as a computer experiment rather than an in-person experiment. We actually know the complete case. Then we have, and this is important because it's not just take a data file and just remove some. The simulation here is actually controlled so that we know we have a very clear sense of the type of unit non-response. So the ignorable MCAR is completely random. And so let's say, for example, we wanted to simulate we simulate 31.89% response. Well, 14,076 individuals out of all 44,135 are selected completely at random. Completely at random. That's completely at random. So missing at random, also ignorable. The unit non-response is dependent on an ancillary variable, in this case, X. So you'll see that there's a relationship between Y and X, and that it is, so when you see the missingness, as we saw here, the missingness, you'll see a relationship between the missingness and X, and of course there's a relationship between X and Y, but there is no missingness to Y. So that would make it MNAR. So in the MAR case, unit non-response is dependent on the ancillary variable X. So you could say, well, individuals on a particular score, some range of scores, maybe at the bottom half, they have, not everyone's going to respond. And so you could do something that in the bottom half of X, the ancillary variable, and yet X and Y are related, and Y is what we're interested in, the MCF score. The non-ignorable, well, this is entirely the case of where the non-response is dependent on what we're interested in itself, our outcome variable, the MCF score. And so this is simulated by having a threshold on Y, the MCF variable, and then only a proportion of individuals set to respond, depending on that response rate. So, so we might say, well, let's say anything below the mean, 50, that's where your large number of non-responses are going to come from. And in that case, that's where you would get your, that's where you get your non-responders out of that area. So you would then, if you look back at the calculations, this is where you would get the sample of unit non-respondents would predominate from, for example, that part of it, so 30,000 there. That definitely would result in a distribution in which the non-response depends on the variable itself. So again, imagine this MNAR reflects this mental health variable, and individuals below a particular value in your MCS have less of a chance of responding. Not everyone's going to respond, and that's where your non-respondents are going to mostly come from. Does that make sense? So some people are still going to respond, but not everyone. That the probability, if you wish, or propensity is not equal along the continuum of MCS scores. In fact, the probability of responding would be less, perhaps, at the lower end. So below that threshold. So let me give you some results for the mental component score and proportion of flagging. Remember, all domains of the SF36 are scored on 0 to 100, and 100 is your best response state. Here I did it, and we actually repeated it 10 times within each cell of respondents. So you'll see here that there is the complete case, the response rates 100, everyone, of course, we have that complete case. Then we have missing at random, and again, the response rate of 7.97%, 15.95, 31.89. Then completely at random, those three, and then missing not at random there. The target mean is 50, the target estimation is 9. That's from the simulation. I know that ahead of time. Standard error target is 0.043, and the values reported are an average over 10 replications at each cell. I mean, we could have done more, but given these large sample sizes, you actually get a great deal of stability very quickly. We did want to do some replication, and so these are the averages over those 10 replicates within each cell of the simulation design. And what you can see is whether it's, and now we have the non-normal distribution and the normal distribution, and we report the mean. Lo and behold, in the complete case, the mean is exactly what it should be at 50. Standard deviation is 9, standard error 0.043. The coefficient of variation, which is often used as a way of the precision of the so yeah, some sort of it's a precision of the estimates. It's measured by using the coefficient of variation, which is calculated as the estimated standard deviation of the point estimate divided by the point estimate itself and expressed as a percentage. So it's 18 here. So you actually take the standard deviation of the point divided by the point estimate itself. So it's 18, which is well, it's mostly allows you to do a comparison across. So you'll see for the non-normal distribution, it's 18, and for the normal distribution, it's 17.98. So you get very comparable coefficient of variation, and then you could even compare it within to see what happens to the precision as the different conditions and sample sizes and response rates. What's interesting is you can look at the standard error, and the first obvious finding that you're going to have is that for the complete case, the standard error is going to always be smaller than, I mean, even here, completely at random. It's going to be smaller. Why? Well, that's sample size. So because we go from 44,135 to 14,076, so you're going to see a difference. And then, you know, we're going to have different kinds of response rates here of MCAR. But even still, under MCAR, you're going to see that, in fact, the standard error. And that's always true. That's true. That's one of the things known, that's kind of obvious out of the literature. If you have only individuals who decided to participate, your sample size is going to be smaller, and therefore your standard error is going to be larger. And that's sort of well known from that point. Well, but look at this. If under the complete case we get 50, that's our target as a mean. Look at missing completely at random. Even for the non-normal distribution, they're all extremely close. I reported just 3 decimal points just to give you a sense of accuracy there. But look, it's the same thing here. Missing completely at random. Missing at random, the ignorable case, you also get the values. They're a little higher here, but not too much, actually. They're quite, these seem large, but they're actually, the difference between them is quite small. You can see the standard deviations, standard errors, and the coefficient of variation. What's curious is look what happens with MAR here. Look at the means. That's interesting. Let's take a look at some of these through some graphs. And here I want to make a point that's very important. This is for the non-normal distribution. I want to look at the comparison of the scale of the x-axis. And one of the first things, and these are the means here. So these means from this chart are now plotted here. This is for the non-normal distribution. Well, first of all, look what happens with the response rate and the complete case. Well, this is 0 to 55 range. It could even be 0 to 100, but I only chose to do it to here. They don't seem a lot. If you zoom in here, then they seem quite larger. But remember, you're zooming in closely into this TID area when I plot it from 49 to 55. So basically, I'm zooming in to this range here of the distribution. So I zoom on in, then you can see it, the same data there with a different scale on the y-axis. I wanted you to give a sense that actually, if you look at a larger range of possible scores, the difference is not large. But when you look at it, you still see a difference. You can see that, in fact, the complete case is here. That's that blue dot. Missing completely at random is this bottom line there, which is close to this, the complete case. Then there is a small positive increase for missing at random, and then a larger difference from the complete case or the 50 when you move up to missing not at random. But these lines are very flat, so the response rate isn't playing a very big role here. Same idea here. I wanted to give you a bit more of a range, then I wanted to zoom in, right, from 49 to 55. And again, the same pattern you'll see here, right? Missing completely at random, missing at random, missing not at random. And there's about a 3-point difference. If we compare the distributions, the pattern of the two distributions is the same. It's a bit more of a bias for the normal case, and that has to do with a lot with, if you look at the distribution itself, you'll see that, in fact, missing not at random, but it's not a large, it's like half a point. Let's not lose sense of that. So they're but the pattern is the same, right? This missing at random, these are both ignorable, so you do get a slight inflation compared to the whole case or the target of 50. But you get about a 3-point to 2.5 point. Is that a big difference? Well, it's hard to tell with the mean. Certainly there's a difference. The standard error is going to be quite different, as we saw here. The standard error is going to be quite different, but the mean itself, you'll see a small effect. When you look at the missing data mechanism, though, you do see something quite interesting. And again, the response rates are nearly indistinguishable. So you'll see that they're really, which is the point we're making here, they're pretty much flat. You'll see the complete case, you'll see missing at random, missing completely at random, which is very close to the complete case, as we saw before, and the missing not at random. There is a bias, a positive bias. And there's a bias also here in the normal case, but the pattern is very much the same. If we look at the confidence intervals, though, now we'll begin to see a bit of a difference. So this is the conventional so again, remember all of these analyses, we have unit non-response and we are using the complete case analysis, the ad hoc analysis. We are not doing anything to adjust for unit non-response, right? Let's say we were one of the 81% of epidemiology or social health science kind of studies. That's what all of this was about. And that's what the confidence interval is as well. And what you'll see is if our target is 50, missing complete at random actually captures the 50. Again, these are 10 replicates within. And that's regardless of the response rate, but missing at random doesn't. And so confidence intervals, now we're beginning to see a slight difference. Point estimate in the confidence intervals. Now the confidence intervals actually no longer contain 50. And for the moment, we need to get away from this notion of they're close. There's no close here. They either contain 50 or they do not. And you'll see the only ones that do are in green here. They're missing completely random, regardless of the response rate. All right. So let's now take it to another use, which is they take the mental component score, and we're now going to dichotomize it at a cutoff of 38. And that number comes from this article here in 2016. I mean, we just want to make something very plausible. And it's to identify the presence of either depression or anxiety, and it's just as a flag to be able to trace or track either across time or across domains the proportion of individuals who are sampled who have this depressive symptomatology. Well, here's our main result. And you can either report it as a proportion or a percentage. And you have it for the non-normal distribution and for the normal distribution. They're going to be different because for the non-normal distribution, the cutoff results in an 11.14%. And for the normal distribution, it's the 9.09%. And again, here you actually have something quite interesting. Because if you look at, doesn't matter, percentage or proportion, remember, because I report 3 decimal points here, 0.112 becomes 11.24%, meaning there's a 40 here. That's hidden because I did it to 3 decimal points. But let's just use a percentage. What's very interesting is, let's look at the non-normal case. In the population, it'd be 11.14%. If you look at the MCAR, the point estimates are really close to that value, regardless of, that doesn't matter what level of response rate. That's a very small 7.97% responding, right? That's enormous. Doesn't make much of a difference for MCAR. What's interesting, though, is you get a deflation in the number when you go to MAR, and even further when you go to MNAR, because MNAR is based on the variable itself. So the means seem to not be too affected, but they certainly are affected when it comes to this proportion. That's very interesting. Same thing under the normal distribution, where it's about 9%, 9.09, and you'll see under MCAR, as expected, you're going to get a point estimate that's close to the target of 9%. Doesn't matter the response rate, but look what happens when we have MAR or MNAR. Even MAR, the ignorable, you still get a reduction. So you would report if there was, let's say you had a 31.8% response rate, and the unit non-response is due to the mechanism of missing at random, you would get 6.42. When in the complete case or in the target of the population, it's 9%. And look at that for a missing not at random. That actually reminds us now that not everything is happy here. Proportion is a slightly different. Think of the proportion here as a average, where everyone is given a 0 or 1 based on a categorization of depressive symptomatology or not. So it is still an average, but it's an average of a binary variable. So it's a different kind of statistic. And look what happens. You can actually get quite a big effect, even under MAR, The confidence intervals, conventional kind of confidence intervals using, so imagine you ignore the unit non-response. MCAR, your confidence intervals contain our target, 0.09 or 0.11. And here I just did it as a proportion. But even under, look at this, even under MAR, we're not capturing our target. And again, this is 10 replicates within. I pushed up the number of replicates given the sample sizes. You're not getting much of a difference at all. And that's the same with MNAR. So our confidence intervals are, they don't capture the population target. They're wrong. As are our point estimates. So it's more pronounced in this than it is in the mean of the variable. It's just that the scale is different in the mean of the variable, right? So it's harder to see these effects. But in the proportion, the obvious effects are right there. So some remarks based on the simulation results of the mean of the MCS and the percent flagged. When naively ignoring the unit non-response and analyzing the variable data, the complete case analysis. Well, first of all, I want to say something about response rate. From the report on the mean of the MCS and the percentage cases flagged, depressive symptomatology, we conclude that the response rate percentage was not as relevant as the type of non-response observed, the non-response pattern. So you'll see that, in fact, as we said, response rate is not playing an enormous role, not even barely an important role at all, in either the mean or in the proportion. And don't forget, this ranges from 31.89% to just under 8%. So we cover a large span in there. The second is variables related to non-response patterns, as we observed in the results. When unit non-response is non-ignorable, MNAR, there is clearly an impact, and the impact is very visible. There's also small impact in the ignorable non-response due to MAR. And I want to highlight these. These are actually not distinct classes. This is one of the subtleties needs to come across because of Rubin's very, very capable, very interesting and very, I actually think, nuanced mathematical view. These are not actually distinct. I mean, it's not. I mean, MNAR is MNAR. There's no doubt about it. But it's really missing completed at random. These are not distinct. There's actually almost a points of a range of possible mechanisms that one could characterize. So there's not exactly, these are not necessarily distinct categories. But the key thing is response rate was not important in determining the outcome, but the variables related to the response patterns, that is the causes, were clearly important. And in general, the shape of the MCS distribution played a minor role. So please note, if the missingness, that is unit non-response, was simulated as arising in the upper part of the distribution rather than the lower part, which we did, the proportion would be inflated rather than deflated. So we saw here that the proportions were deflated. Well, that's partly due to the fact that when we simulated it, we actually induced the simulation, the non-response at the lower end of the distribution rather than the higher end. If we had done it on the higher end, these would have been inflated instead. So I don't want you to leave with they're always deflated. compared to the 9% there, right? The 5.3. Instead, it depends on where that non-uniformity is concentrated, on the lower end or on the upper end. Here it's on the lower end, which deflates it. Had it been on the upper end, it will inflate it. So that's an important thing to keep in mind. All right, well, let me see a few words now about the regression case. So these are analytic studies, the fitting of regression models with unit non-response data. So a few words about the simulation of the analytic study, or the analytic survey. As was noted earlier, most surveys at statistical agencies are conducted with a descriptive inference in mind. They aim to estimate means, totals, ratios based on the measured variables and change of these parameters over time, or even sometimes over subdomains. The simulation results so far in the webinar reflect these kind of descriptive inferences about the means or proportions. With the growing interest in the use of statistical surveys to fit statistical models, using regression, structured equation modeling, or more complex mixed models, we now turn to a simulation of an analytic study of regression of the mental component score onto 3 predictor variables. A new twist here, a new twist to the simulations that allows us to investigate the effect of unit non-response when the regression model is not correctly specified. Small sidebar, computing the mean or the proportion is also a model, except that it's a model that is not as, I'm going to say this, it's not as parameterized as a regression or a structured equation model or a mixed model. The parameter is really one, and in either case, and it's governed in a very, the model is a very simple model compared to multiple regression models or mixed models or structured equation, where these are hyper-parameterized models. In a location model like the mean or a proportion, there's this notion of model misspecification doesn't play as much of a role. In some extent it does, but just to be clear, regression is nice because it allows us to now deal with whether a model is correctly specified or not. So a bit more detail about the simulation. We use a widely used simulation approach. For example, see Allison's paper in 2000, but there's many others. To compare computing the naive estimates, ignoring the unit non-response, we generated, again, 44,135 observations on 3 variables, x1, x2, and x3, the 3 predictors. Because the primary concern is with bias, large sample size is designed to minimize the sampling variability in this case, and it also matches the simulation from the mean and the proportion. x1, x2, and that should be x3, forgive me, that's a typo, x1, x2, and x3 were drawn from a bivariate normal distribution with a correlation of 0.30. Thus, in the observed data, x1, x2, and x3 each have means of 0, standard deviations about 1, and a correlation of about 0.30. Y is then computed from the equation in this manner here, x1, x2 plus x3 plus u, where u is a disturbance or error term, and is drawn, in our case, from a standard normal distribution independent of x1, x2, and x3. And this is sort of standard statistical layout. Notes the model that generates the full data. Increasing the variance of the error term allows me to change the R squared, of course. That's kind of one obvious way of and changing nothing else except that allows me to very easily control it. Please note that all the variables were simulated as standard normal z-scores. The mean of 0 for the variables imply that the B0, the intercept, is 0. As such, the B weights are also standardized B weights. They have a mean of 0 and standard deviation of 1. And so that the weights I chose is 1.0 times x1, 2, x2, and 30, x3. And Increase the variance of the error term allows us to change the R squared for the model. In our case, R squared is 0.250. What you see here is you have one variable that has a B weight at 15 or 30 or 15 times larger than either of the other two. That allows us to get a sense of you have X3 is something, if you wish, that is an extremely important variable in the regression analysis. And these ones are less so. Standardized B weights are not the best way, but you'll see it in the Pratt index that I'm going to show in a moment. I'm going to look at model misspecification because model specification relies on the concept of a functional form, which refers to the algebraic form of a relationship between a dependent variable and regressors or explanatory variables. Again, let's not get into the technical mathematics too much, but get in the sense that you're fitting the same. Suppose one fits the same variables, the same functional form as the model generating the data. In that case, we're in the case of correctly specified model. Otherwise, a mismatch between the generating model's functional form and the model being fit results in model misspecification. And of course, there's an infinite number of ways that something can deviate from the generating model. I just chose a couple of them just to make a point here in a very simple way. But it's correctly specified if the regression model generating the data has the same form as the one being fit. So if generating the data is this model here, 1.0x1, 2.0x2 plus 30x3, then, and you run a regression in which you, in essence, say the functional form is you have y, and then you have some b1x1, b2x2 plus b3x3. That means it is correctly specified because there's a match in form between the model generating the data, or producing the data, and the model that's being fit to the data. We then created the desired proportion of observed responses to missing as unit non-response according to 4 mechanisms. And given that the response rate was not found to play a role, and for the mean and proportion, we chose to only simulate the case of 31.89% response, where 14,076 of 44,035 participated in the survey. And we continue to have 10 replicates per cell of the simulation design. And again, we found conversions very quickly, particularly given the large sample sizes. We're simulating unit non-response, again, the same way. Unit non-response is completely at random. In the missing at random situation, the unit non-response is missing not at random, and the X variable and the source is X3, and the variable with the largest population, which in this case was the largest population B weight. So what I decided to do was to make this the variable that's related to Y for the missing at random case, that this is the variable, some value here would be the determining value for the missing at random. If you go back and look at that diagram, that's what I'm talking about. The type of missingness is related to X3, and X3 is related to Y. But the type of missing rate is not related to Y directly. And then missing not at random is when the missingness is as the source is the outcome variable Y. So if you look at that diagram we had before, that's the kind of idea we had going from that earlier on in today's webinar. So missing completely at random, missing at random ignorable, missing not at random non-ignorable. We're going to report the R squared for the model, the standard error of estimate for the model, B weights and their standard error for each predictor. And when there are multiple predictor variables in the model, a value of what's called the Pratt index. The Pratt index quantifies the unique proportion of the R squared attributable to each X variable. And it's a method developed by Roland Thomas in collaboration with myself and Ernest Kwan, Ed Hughes, and others. I think the place we discussed it a great deal in regression. It's in 2018, the paper by Roland, Ernest Kwan and I really talks about the mathematics of the Pratt index and a bit more in the social indicators research, and I talk about it in this chapter and validity as well. Well, take a look at what happens when the model is correctly specified. So the generating model, the model fit have the same functional form. So the generating model is y equals some function of x1 plus x2 plus x3, and you estimate only in the b weights, and the model being fit the data is exactly that. It's some function of x1, x2, and you're just estimating the b weights. Don't forget, the b weights are 1, 2, and 30, and the r squared is 25 in the generating model. Well, look at this. The r squared for complete case, 0.25. This is very much what we were expecting, and there's the b weights. Are they close to 1, 2, and 30? The standard errors and the Pratt index, where 96.7% of the r squared is attributable to x3, which is the one with the largest b weight. Please don't forget, earlier on I said that these x's are correlated, intercorrelated at about 0.3. These are not independent. They're correlated at about 0.3. I could have gone higher, but I thought it gives us at least some correlation among the x's. And so a couple slides ahead. Take a look now at MCAR, r squared. Okay, so it's within. It's actually not that far off. It's a slightly higher, but very, very little. Standard error, of course, is just a little bit higher. These b weights, 1, they're very close, and the Pratt index always mirrors it that way. Look at the MAR dependent on x3. Look at that. R squared 0.271. B weights. So, but what should surprise you somewhat is even in the case where it's missing not at random, the coefficients are not there. They're a little lower, there's no doubt, but it's not the massive effect that you're seeing. And the R squared is higher at 0.27 versus 0.25. There's no doubt about it. Sample size is different, etc. But what you can see is when the model is correctly specified, the B weights and Pratt indices of variable importance are fine, even with MNAR. Likewise, the R squared is almost the same for MCAR, MAR, and MNAR. Of course, the smaller sample sizes will affect the standard errors in the R squared compared to the complete data and to the population, if you wish, or the generating function. What the curious is that the model is robust when correctly specified. And this is a key concept in the statistical theory of modeling. People who come from a modeling tradition far too often forget that if your model is correctly specified, then there is a sturdiness to the model, there's a robustness. Of course, fundamental problem is that we never know. Well, we'll never know in practice whether the model is correctly specified. It's really hard to determine it in a precise way. You can gather information, you can develop theory to support the kind of model. And if anything, this speaks against just the ad hoc use of model building, thoughtless automated model building. Instead, the analyst needs to have some sense of what's being modeled, about the process, etc. But what's fascinating to me is that it's not often realized that if your model is correctly specified, you have a certain amount of sturdiness to it. We can also have incorrectly specified. In this case, the generating model is the same one, x1, x2, x3, the same code, but it's the model that's being fit only has x3 in it. And look at this. Again, the B weights, the standard errors, R squareds are actually, even for MNAR, pretty good. Why? Well, when the model is incorrectly specified, but the X variable with the largest, by far, B weight is fit to the observed data, the observed data that has non-response, then the B weights are fine. Well, there's only one B weight. The B weight for X3 is fine and consistent across there. Likewise, the R squared Of course, the smaller sample sizes affect the other. Model is robust when nearly correctly specified. And this is, I'm going to use the word nearly here. A lot more work. There is some work in this area in statistics. A lot more work needs to be done to develop this kind of thinking in the area of data analysis and day-to-day data analysis practice. But if you have the most important variable in the model, and in this case, that's why I chose this, is definitely, without dispute, 30 has the largest B weight, and if you wish, is the largest Pratt index, and most important variable by far. Our B weight's going to be okay. In fact, your R squared's even pretty good, and it's sturdy even to missing non at random. Complication, of course, is in day-to-day data analysis, far too often we use really ad hoc model building approaches. This really speaks to the fact that it's really important to have a sense of our process, the phenomena that we are modeling, bringing content specialists in. It's not just about running software. Really, if you have a good sense of the theory, the models from past analyses, other domains, etc., this could help you get a sense of whether even your naive, really really not a good use to just on a day-to-day basis use this kind of analysis, but even complete case will give you something that's reasonable. But the point I'm trying to make is the model has to be correctly specified. And I mean correctly specified, right? And in this case, it's close, meaning because it's the biggest variable, is that it's a very unique kind of situation. Well, what if you did this? It's generating is the same, but now you only took the two, if you wish, really not major drivers in the regression analysis, most important variables. Well, you can obviously see the R squared's off, the B weights are off. I mean, they're similar to each other, which is a curious finding. And there is the literature in mathematical statistics points to some of these issues. Comes a little bit as to how one conceptualizes, are you in a finite model case? Are you in an infinite population case? But the key point is that the generating model is quite different than even the complete data case. Even the complete data case is wrong. Why? Because it's only those two variables in this case. Some remarks on the simulations of using naive complete case analysis. The big driver here is model specification. An important but seldom discussed concept in analytic statistics and analytic surveys is the matter of model misspecification. There is discussion of this in the literature, but I think a lot more of it has to go on. Of course, in real data analysis settings, we do not know the data generating model. Some exciting advances in the field of statistical research on approaches to trying to get a better sense of model specification from your data. A heck of a task, but there is some work in this area. But I want to highlight for data analysts that if you happen to have the right model, if you spend a lot more time on the modeling, that can actually give you strength. That can give you strength. So, of course, in real data, we do not know the data generating model. When the model is correctly specified, unit non-response most likely not cause dramatic change in the parameter estimates when the supposed cause is M nor or bar. Missing not at random is usually considered the worst case scenario, but the model can step in this case, if it's the correct model. We'll leave that as a point. This is not the only place where this is seen. It's important to note that models can bring strength to data analysis in correct models in a lot of other settings. There's a paper by Anat Zeit and I in 2013 in which we again demonstrated a point about mixed models, particularly when they're used for trajectory analysis, and claims are being made about how these models give you robustness of all sorts, but that's only if the trajectory is correctly specified, the model of the trajectory. So it's a point that's being made again, and it was made separately in 2013 with a different kind of model by at the this was done when, not Zeidman Zeit, when Dr. Zeidman Zeit was a PhD student working with me at UBC. So let's now talk about the take-home messages and observations transitioning to webinar 3. And I want to integrate some of our what we saw in simulations with findings in the statistical literature. Main message is that ad hoc solutions, complete case analysis, are not a good idea in general. A good idea in general for data analysis practices. The simulations in this part of the webinar were about the use of complete data analysis in the presence of different kinds of unit non-response. Places where complete case work well are idealized settings, which will likely rarely, if ever, know whether we are in those settings. For example, a correctly specified model, or a setting where the difference between respondents and non-respondents on the variable of interest are very small. We're going to talk about that in a little bit. You're going to see this. These are the two settings in which you're going to see that, in fact, complete case analysis works well, but we rarely, if ever, know these idealized settings are where we're working. The settings where ad hoc methods work rest on assumptions that are not completely verifiable from observed data. And that's really instead of ad hoc solutions, we recommend the methods described in part 3 of this webinar. So you'll sometimes hear in the statistics literature that complete case analysis can sometimes work. The problem is sometimes work. And what I want to point out here is there's actually two kinds of settings. One of them is when the model is correctly specified. And you're going to see in a moment that the other setting is where the difference between respondents and non-respondents on the variables of interest are very small. That difference is very small. So instead of the ad hoc solutions, we recommend the methods described in part 3 of the seminar to adjust for unit non-response. Another bit of take-home message is typically the response rate is used as a pointer or proxy measure of non-response bias. The common assumption is that the higher the response rate, the lower is the non-response bias. This, however, is not necessarily the case. In considering the effect of unit non-response for statistics such as the mean or proportion, Gross in 2006 showed a very useful and simple deterministic model where he showed that the non-response bias is a multiplicative function of the non-response rate, and the difference between survey respondents and non-respondents with respect to the variable of interest. So if we're calculating a mean, the bias is a multiplicative function, so it's the non-response rate times, for example, the difference in means between, so let's be very concrete. We, in our simulation, looked at the MCS score. The non-response bias in the mean is a multiplicative function of the response rate times, right, that's multiplicative, times the difference between the means of the respondents and non-respondents on the MCS score. And you actually saw that, in fact, non-response rate was not, in fact, a major determining factor, that it was the difference between them. And the difference, when you'll see, when we simulated, the difference was not very large, even in the, I mean, it was a bit in the MNAR case, but not a large effect. When you turn that into proportions, then, right, so everything is 0 and 1, where the cutoff was, then we see that, in fact, given where the cutoff was, that, in fact, yes. Again, a proportion is a mean of a binary variable, if you wish. Then it's a non-response bias is a response rate times the difference. And there, in fact, that you will see that there was some impact in our case. Building on Grove's ideas, information from the second factor determining non-response bias, the difference between respondents and non-respondents with respect to certain survey variable, or the covariance between the survey variable and the response probability, is not normally available. We don't know the mean of the non-respondents because they haven't responded. So by definition, we don't have that. Instead, we have response rate. And so we'll often try and make decisions of whether, we're in a safe situation or not with unit non-response by focusing on what we do have, which is the response rate. But, and we'll often say, well, what is a minimum response rate to say, okay, we're in a safe zone to just use conventional unit non-response? The answer is the answer is that it actually doesn't work that way. We can see, however, from our simulation findings that giving oneself a pass and not concerning oneself with the quality of the statistical survey based solely on achieving a certain minimum response target, other than 100% participation, is not justifiable. There is no response rate other than 100% that is deemed to solve the non-response problem, because no non-response bias is to be expected. So that's a very complicated sentence, but basically, because it's a multiplicative factor of both the response rate and the difference between means, for example, in that descriptive analysis, response rate alone doesn't do it. You could have you could have a very high response rate, very small non-response, but a big mean in differences, and your mean will be biased, right? Because it's the non-response rate and the difference between the survey respondents and non-respondents on the mean, for example. Well, you could have a response rate. So you could have a non-response rate of like some very small number, meaning a lot of people have responded. But if the differences between the means is larger, then it's very large, and you still could have a lot of bias. So it's a multiplication of the non-response rate and the difference between means, right? It's that multiplication that gives you non-response bias. And so you could have a really, really high response rate, but a big differences in means, and you're still going to get a lot of bias. Gross's point that non-response bias is a multiplicative function of non-response rate and the difference between, for example, the means. So it'd be the non-response bias in the mean is equal to the non-response rate times the difference between the mean of the survey respondents, and non-respondents in our variable of interest, for example, the MCES variable in the mean or simulation, becomes very useful as we move to our point that this idea actually helps us understand a little bit, this non-response bias, this is where it's helpful here, is giving a little bit more information of what should we focus on. So building on Grove's idea, his ideas, information about the second factor determining the non-response bias, the difference between the respondents and non-respondents with respect to certain survey variable, or the covariance between the survey variable and the response propensity, that is not normally available to us. Because, why? Because all we have is the variables that the scores that from the respondents in a typical observational type of survey. When in practice, a statistical survey, we don't have that. We don't have the information from the people who haven't responded. We, in essence, don't know what we don't know, if you wish. So the difference between respondents and non-respondents on, for example, the mean of the MCS, that's not available. It's not normally available. So practitioners will focus on the things that they do know. So you read recommendations about minimum response rate, because that is quantifiable from statistical surveys. We have we know how many surveys were sent out, if you wish. We know how many responded, and that gives us our response rate. And from that, people try and get some guiding principles as to when they're in a safe zone or where they're not. We can see, however, from our simulation findings that giving oneself a pass that is not concerning So for the quality of the statistical survey based solely on a certain minimum response target, other than 100% response, which means no unit non-response, that's not justifiable. We have no justification. There is no response rate other than 100% participation that is deemed to solve the non-response problem, because no non-response bias is to be expected. I mean, that's kind of an interesting point, and Groves's equations helps us move forward. Another take-home message and some observations is that it's important to keep in mind that the unit non-response has two main consequences on our data and our data analyses. The first is because the number of observations is less than initially planned due to non-participation in the survey, that is unit non-response, then unit non-response increases the variance of the estimation. Right? So the standard errors are going to be larger because the sample size is smaller than initially planned, right? That's kind of a first consequence, and that's kind of obvious. If not everyone's participating, our sample size that we're going to be analyzing via the sort of conventional, this using the complete data kind of strategy, your standard errors are going to be wrong. And as we saw in the previous slide, unit non-response introduces a bias in the estimations if the measured variables differ between respondents and non-respondents. But again, we do not have that kind of data. But it's important to keep two things in mind. Automatically, the standard errors are going to be larger. That is, the variance of the estimation is going to be larger. Right? Why? Because the sample size is less, because you have people who have not participated, compared to the complete case, right? And second, we could get biases. Another observation I want to make is sort of a take-home message is comparing respondents and non-respondents on ancillary variables will provide patterns of associations and observed differences, but it should not be used. It should not be used to determine the missingness mechanism. And that's a should not be used to determine the missingness mechanism. So what can be learned from the missing mechanism from observed data? Well, actually very little. I mean, some people will compare respondents and non-respondents on ancillary variables, right? So you have the survey, let's say we have the SF36, we have the items in the subdomains of the SF36, but we only have some number of respondents. So let's say 14,076 out of the 44,135 that we sent out. But we have ancillary data, ancillary variables that we may have done through a unique matching variable and from some other data set, simple administrative data or some other data. Those other ancillary variables should exist for both the respondents and the non-respondents. So those who chose to participate, those who chose to not participate. Sometimes people get quite excited by that. They say, okay, I can now learn a little bit about the difference. You can, but not what you think you can learn. Like a lot of individuals say, well, this will let me know whether I have MAR, MNAR, or MCAR. And the reality is, we'd like to be able to rule out MNAR because several well-known and widely used methods are valid under MAR and MCAR. Right, so we want to be able, but the fundamental problem is that generally if one had evidence against missing complete at random from the ancillary data, we cannot disentangle if the mechanism is MAR or MNAR, because MNAR requires you having the data which you don't have, because missing not at random by definition is the variable itself. So in our case, we had the depression variable, and we said individuals who were low, what we simulated, scored low on that variable, tended not to respond. Well, we don't have that data. And so we can't compare the MNAR and MAR data, the respondents and non-respondents, to find out if it's MNAR, because that's what MNAR means. So we can learn things from looking at ancillary variables, but be very careful. You really are not able to determine with any confidence the mechanism. There's little tests, little as in LITTLE is Rod Little, an eminent statistician. And they're available in some software, but again, be very careful. You're not going to be able to determine all of the be able to rule out mechanisms. And the other thing too is you may have sample size limitations, you may have other issues that really limit the conclusions you can make in terms of the mechanism. So be careful. So I'm going to close now today by transitioning to part 3 of the webinar. The first point I want to make is when survey data are being analyzed, it is common to formulate research questions in terms of statistical models fit to the survey data, which nearly always involve non-participation. The data always have some unit non-response. So when survey data are being analyzed, it is common to formulate research questions in terms of the statistical models that fit the survey data, which nearly always involve non-participation. And this becomes important because this is the sort of analytical surveys that we're referring to. Surveys that make inferences on all parameters, or as I said, are these analytic survey studies. In contrast, descriptive studies are conducted to estimate means, totals, ratios, etc. Those are the common ones based on measured variables. One will see reference to finite population characteristics in the survey statistics literature regarding the descriptive surveys. Be aware of that. It gets a little murky. You really need to spend some time to understand what are finite populations versus infinite population models and superpopulations and other such things. Commonly used statistical models in analytical surveys include linear regression, generalized linear models like logistic regression, and mixed models, such as hierarchical linear models or mixed effects models. When research questions are formulated in the statistical language, in this kind of statistical, data analysts are commonly interested in the statistical model's parameters. Now, I bring this up because one can think of populations satisfying these models as conceptually infinite. So one can think of the population satisfying these models as conceptually infinite. You will see in the survey statistics literature that is often assumed that the values in the finite population from which the observed survey sampled units were selected are outcomes resulted from sampling from this infinite population. It's important to note that the survey may or may not contain variables related to the survey design. So this is important to keep in mind when you start doing the kind of analytic surveys, and now you begin to actually bring in the notion of a model. And you'll see in the survey statistics literature, it's often assumed that the values of the variables in the finite population from which the observed survey sampled units were selected are outcomes resulting from sampling from this infinite population. And so, and the infinite population we're talking about, but one can think of the population satisfying these models as conceptually infinite. This is immensely subtle. I want to bring it up as something for you to think about. If one starts to dig deeper into the survey statistics literature. As we've highlighted in this webinar, ad hoc solutions like complete case analysis are not a good idea in general for data analysis practice. There are places where complete case analysis works, but those are very idealized settings. In part 3, we provide an overview of methods for adjusting for unit non-response, with the leaning towards weights and weighting and really propensity score methods. When considering how to adjust for unit non-response using methods such as weighting, as we describe it and demonstrate in part 3, if the regression model affiliate happens to be correctly specified, or you happen to include regression predictor variables that are proxy for the unit non-response mechanism, then there's no need to adjust for unit non-response. Does this happen? Sometimes, and I want to bring this up for you to think about. Now, the first one, if the model is correctly specified, that's not. But sometimes you may have picked up a proxy or variables that are really proxies for the unit non-response. Curiously enough, at that point, there's no need to adjust, as we saw in the case of the correct model. But also, if by coincidence, you've got a proxy for the unit non-response process, then in fact, or if you wish, a quantification of the propensity for unit non-response as a proxy, then in fact, there's no need to adjust. Again, incredibly subtle. How do you know you're in this situation? Again, I would say adjust. I would say do adjustments. I mean, these are pretty idealized settings. Methods that adjust for unit non-response, weighting using methods in part 3, are intended to correct for variables that may not have been included in the model, right? So weighting for non-response is a natural extension of weighting for sample selection. In our case, in part 3, recall that we're actually only adjusting for unit non-response. We're not doing, if you wish, the double expansion, which is also then correcting for complex survey design. We want to keep it manageable and simple for any analyst to be able to say, okay, let's for the moment deal with a simple situation. We have unit non-response, but we don't have any complex sampling situation. We have a sort of a simple random sample happening. Idealized, yes, but you get a flavor for how to do this kind of work. So this weighting for non-response is really a natural extension of weighting for sample selection. Design weights are commonly adjusted for many different reasons, such as compensating for unit non-response or for calibrating to known totals, et cetera. So this falls within that category there. I want to thank you very much for your time. In part 2, I hope you have a sense from all of this at the impact of unit non-response, and that the statistical literature is somewhat subtle, and that the statements about the impact of unit non-response are a bit subtle because it depends on whether you're in one of these idealized settings. As advice, we advise that you now move to part 3 and learn about adjusting for unit non-response. And Pamela will talk you through various methods, some theories, some very nice, elegant ideas of how to think about missing not at random, but also go through an example case of using R, or using commonly widely available program like SPSS, but not just any SPSS module, the complex analysis module. But first building a quantification of this propensity to not respond. Remember, we began with this. There is a propensity. Every sampling unit, every person in our survey, if you wish, has a propensity to non-respond. We can quantify through a probability. How we compute that probability, what we're going to lean towards, what Pamela and I are leaning towards, is to use propensity score methods. Thank you very much.